Okay, great. So, first of all, thanks to John, Vivian, Rachel, the other sojournistas, right? Sojournistas for the venue and for the hospitality. Thanks to Laura for inviting me to talk. I think we've been talking about this back and forth for I'm not sure how many months, but she was finally able to slide me in, so I'm happy about that. So this is the starting point. So I'm hoping that this is going to be interactive. So I will ask questions, and if people have the answers, you can raise your hand or you can shout out. Feel free to interrupt me as I'm going. I'm happy to stop or explain things. I've got an agenda. It's broken up into chunks. And so since this is the idea here of the workshop is that all of you folks are going to kind of be doing this along with me, and we're going to be learning together. I'll have some breaks, so if people fall behind a little bit, want to catch up, it's normal, it happens. So, so I think there'll be some opportunities to do that. This is interesting for me because, so first of all, this is the very first time I've ever presented this. It's actually the very first time I've ever done a workshop. I've done presentations before, but I've never done workshops. I'm not quite sure how the dynamic's going to work, so we'll have to see. And the subject matter is something that kind of, well, I wouldn't say that, I certainly didn't develop it myself, but I've participated in many deep learning and machine learning meetups and taking online classes and all that thing. And this is a sort of a methodology of going about it, which I haven't seen anywhere. And I was doing a lot of research on the internet to see if anyone has kind of gone at it from this angle. And I couldn't find anything, and there's actually a good reason for that, and we'll talk about that. But I thought it would be interesting, so I kind of dove into it, started exploring it, found some things that I thought were fascinating. So hopefully you'll find it interesting. Actually, one of my concerns is that I'm actually not sure what the knowledge level of everyone in the room is. I'm sure some people are like experts, and other people have told me already that they're novices. So this is the content here is geared towards people who are not familiar with neural nets. But even if you are, maybe you'll find some things that are interesting in there. So, okay, so that's my intro. Let's go to, let me get up the presentation here. All right, so that's me. That's, my name is Mark Kramer. I'm Applied AI Product Manager at Xerox, and I work at Park. So, here's the agenda. Oh, a little bit of a delay there. So, I won't spend a lot of time talking about myself or talking about AI, machine learning, deep learning, because there's a zillion places you can go for that. But I want to make a little bit of an intro there. But there's actually a lot of material to get into, so I want to kind of get to the nitty-gritty as quickly as possible. And so we're going to build some perceptrons, we're going to wire them up, we're going to train them, test them, and hopefully be able to look at the inner workings of these perceptrons to get some intuition as to exactly how they're working. So, okay.
Can I make a comment?
Sure.
I saw your code, and you obviously know what you're doing.
Okay, well that's very flattering. Thank you very much. Yeah, so all of the materials will be made available. Actually, there is a GitHub that's available. People can go to it. It's not up to date. I will update it. So all the materials will be made available. But you should take copious notes anyway, because why not? So, okay, so I mentioned that I'm at Xerox. So I'm going to start off just talking a little bit about myself. Xerox makes printers and copiers, but I'm the product manager for Applied AI, so how does that work? So I'm actually at PARC. PARC stands for the Palo Alto Research Center. For folks who are not familiar with PARC, here are some of the things that they have developed or invented over the years. It's kind of an amazing list. Everything from, so what do we got here? We got laser printers, object-oriented programming, the GUI, natural language processing, fiber optic cables, optical storage, collaborative filtering, and this is in fact the first personal computer, the Alto. So If anyone finds themselves in Palo Alto, there's actually a really clever, neat, mini computer history museum in the lobby at Park. I think anyone can go check it out, and you can see some of the stuff, and it's worth half an hour of your time. So, this is where my story starts. So, looking around the room, anybody know what this is?
Yeah, even without my glasses.
Okay, so this is the Apple II computer. Anyone know what language used to program the Apple II computer? Basic, which stands for? Anyone? Do you know?
Something all-purpose.
Beginner's all-purpose symbolic instruction code. So, basic. Last question, a little pop quiz. Anybody know how much memory this thing shipped with?
64K.
Shipped with 48.
48, okay.
Yeah, the extra 48K of memory with the language expansion card, you get extra 16K, bring it up to 64. So the address space was FFFF. So there you go. I went to school here, and I initially started off in computer science, but I took a class where we built this thing, and I don't know if anyone's ever used a bread box to build anything, but this fascinated me, and so I switched to electrical engineering because hardware is hard.
Yes.
That's why. But while I was there, I actually took an AI class. I'll share with you that that was in the 1980s. So, Patrick, I actually have the textbook. It is here. I still have it. It's fascinating to flip through. There are chapters on things like computer vision, natural language processing. So a lot of this stuff has been around for a while, right? But it's gotten really hot recently. And I personally believe there are two reasons for that. Would a new person like to suggest why they think that all of a sudden machine learning and deep learning are becoming so in the back? Go ahead.
This is a lot more accessible nowadays than it used to be.
Accessible how?
The tools.
The libraries, the algorithms?
Yeah, and the processing power.
Okay.
And the availability of more data, which
So-
is another.
I think, in my personal opinion, I think those are the two. It's processing power, specifically GPUs,
Yes.
and data. So we're actually going to build some simple networks, and you're going to see that it takes a lot to train these things. And so this is not something that you could do on the Apple II. Well, you could have, but maybe it would take 100 years. So I went to business school, and then since then I've been doing businessy type things. So I've been doing product management for the last couple of decades. But I've kind of kept in touch with that inner nerd and the software side of things, and because computers just generally fascinate me. And so a few people in this classroom have told me that they've taken Andrew Ning's Coursera class on machine learning. I took that, it's fabulous. I couldn't recommend it more. I actually also took the Udacity Nano degree in deep learning. Also would highly recommend that. I was actually in the very first group to go through that. There are a lot of kinks, I'm sure they've all worked out by now, but also would highly recommend that. But yeah, so here, this is me in Vegas developing an RPG for Android, because what else would you do in Vegas? All right, so I'm not going to spend a lot of time talking about all this AI stuff, because there's a zillion places you can go and learn about this. But people talk about artificial intelligence, which has been around since the 80s. It's in this book here. Machine learning and deep learning, and they're kind of subsets of each other. So artificial intelligence is sort of the deep blue, beating Kasparov at chess. Machine learning is, spam filtering, and the deep learning, which is, for me, I feel like that's the most exciting area, and that's what we're going to talk about in neural networks, is things like AlphaGo and so forth. So when you talk about machine learning, this is the formal definition. A computer program is said to learn from experience E with respect to some task T, performance P. If it's performed in task T and measured by P improves with E. Can anyone give me that in English? What does that mean, basically?
Give it examples and expect it to get better.
Exactly. The more data, the better it is, right? So if you have a machine learning algorithm, then the more data you have, theoretically, the better it will do at whatever task you're training it to do. This is another way. I think it's an interesting way to look at sort of the development of these fields, because on the x-axis here you have time, and you can kind of see over time the technology has been developing. And again, I think this is a function of availability of data and computing power. So machine learning and deep learning. I thought this graph was really interesting, which is why I put it in this presentation. I don't know if people have seen this before, but if you want to think, for me, if you want to think about the fundamental difference between the two, it's that guy in the chair. So that person is a data scientist who is doing feature engineering. And essentially what that means is trying to figure out what are the key components to feed into the machine learning model. What are the elements of the data that are critical, and focusing in on those. Whereas with deep learning, that person is not there because the networks just automatically figure out what is important. And we're going to see some examples of that. This is another, so I've got two more slides on the whole before we get started with the actual coding. So when I saw this, I immediately bookmarked it because I thought, wow, this is really interesting. So the old way of writing software was you had some data and you developed a program. The program acted upon that data and it produced an output. And sort of the new way is you have some data and you have the output that you want, and then the computer produces the program to match the data to the output. So put another way, this is a slide from Andrej Karpathy, who's at Tesla, and he gave a presentation a few months ago. And I thought it was another really interesting way to look at this. So in software 1.0, which was the old way, in the space of all programs, you would write a program and it would do a thing. And that is that dot right there. So if you wanted to achieve a goal, you write the code runs, it does the thing that you programmed it to do. In the software 2.0, I'm not sure if he coined that term or not, but let's give him credit. Okay, there's a space, essentially you create a model which covers a space of possible programs. And then with the data, you optimize that model, and the actual output of the model is going to move along a curve of optimization to a point in the space. So, any questions about that? What could be more obvious, right? Okay. So, how many people have not seen something like this before? I mean, it seems like it's everywhere with the circles and the lines and the arrows are pointing, and right? So this represents a neural network. And the first time I saw this, it looked fascinating. I was like, what on earth could that possibly be? How on earth could it possibly work? So if you want to build a network, a neural network like this, there are lots of libraries that you can use. People are probably familiar with these, or they've heard about them if you haven't actually used them. There are frameworks. The one in the middle is by Google. I think it was the first, or it's certainly one of the more popular ones. But what you would do is you would essentially install one of these frameworks, and then you'd start building your network using it, and so forth. But that's not what we're going to do today, right? What we're going to do is we're going to build it from scratch. And so that's what I promised in the intro and the meetup. So, so let's do that. So let's first talk about what is the circle. And the circle in the neural network, each one is referred to as a node. So, and there are many different types of nodes. But the most simple kind of node is called a perceptron. And you can actually do quite a bit with perceptrons. And so I will just quickly describe what it is, how it works, what are the mechanics of the perceptron, and then we'll go ahead and do one. So what you'll notice is that the first thing is that there are a number of inputs. And in fact, for any given perceptron, you could have any number of inputs. I started numbering them from 0. In fact, throughout all these slides, I use a 0-based numbering system. Most everyone uses a 1-based, so they would start with x1, x2, x3. The reason I use x0 is because in Python, there's also a 0-based numbering system. So if you have a list, the 0 element is the first element. So this is going to help us later to understand what's going on. But you have a number of inputs, and any number of inputs would be going into the perceptron. And there's only a single output, however. So each node only has one output. And the question is, how do you get from the inputs to the outputs? So the first thing you do is every element going into the perceptron is assigned a weight. So all of the inputs are multiplied by a weight. And the whole purpose of training one of these networks, or perceptron, is to figure out what are the weights, what are the magical weights that are going to solve whatever problem we're trying to solve. So the weights will go in, and the first thing that's going to happen inside the perceptron is we're going to take each input, multiply the weight, and we're going to sum them all together. And this is called the summation, or the hypothesis. The hypothesis, which is why it's often referred to as h of x. And so it's a very simple equation. Anyone in high school can do this. Multiply each, add them all together, right? That's step 1. Step 2 is called the activation. There are many different kinds of activations that you can use. I believe that technically a perceptron has to be a step activation. I'm not sure.
A linear
Does anyone know?
activation. It should be a linear activation.
Well, so I think that's true, but I'm not sure. Sometimes people refer to other types of activations as also perceptrons. But in this case, this is a step activation. And it's also very simple. If h of x, which is all the inputs times the weights, add it all together, if it's positive, the output is 1. And if it's negative, the output's 0. Simple, right? So there are a few vocabulary words that I kind of prompt with this beautiful looking star here. So the process of taking the inputs and moving them forward through the network. Does anyone happen to know what that's called?
Feed forward.
Forward propagation. Feed forward.
Yep. Sorry. Nathan got it. Forward propagation. So let's build it. All right, so everyone's got this, right? I'm going to try to do something fancy here. Let's see if this works. Nope. Nope. All right. Hold on. There we go. Ah, no, I just closed it. There we go. Okay, cool. All right, so everyone is ready. All right, the first thing we're going to do is we're just going to import some libraries. If you don't know what these are, it's okay. It's not important, but these are basically going to give us a few toolkits to use as we put this together.
Mark,
Yep.
for the people in the back, would you mind saying which libraries you're importing, and also can
Sure.
you maximize the lettering on your screen?
Oh, this one here, yeah, I can do that.
Yep.
So if I do,
By zooming in. Can people in the back see that?
No.
No. Okay.
all right, hold on.
There are two backs.
Oh,
The second one already has
I see. Okay.
It's in the front of that.
I see. Thank you.
All right. Is that big enough?
No.
Ne- Oh, bigger? All right.
Demanding.
More?
Yeah.
Bigger than that?
Yeah.
Oh my goodness. All right. If I go much bigger than that, it's going to be tough because I'm going to run out of real estate to do whatever it is that we're going to do. So hopefully that's big enough. Is that big enough? I hope that's big enough. Is that screen in the back? Is that working?
Yeah.
Yeah.
Okay, great. Okay, so we're importing random. It's going to give us some random numbers. We're importing NumPy, which is a library that's going to give us some numerical abilities, just a few. And we're importing matplotlib.pyplot because we're going to do some cool graphs. So when you type it in, if you're not familiar with Jupyter, if you hit Shift-Enter, it'll run. And it'll go to the next cell. If you hit Control-Enter, it'll run and it'll stay where you are. So that's really all that you need to do. All right, so this isn't a workshop in object-oriented programming, but raise your hand if you're not familiar with object-oriented programming, and maybe I'll slow down a little bit on some points. Okay, Jay, anyone else? All right, so a class is like a recipe, and we're going to put together a recipe to create a Perceptron, which is what you can see on the right there. And this will enable us to spin up as many of these perceptrons as we want by just following the recipe. And so you start by this with class perceptron. And then what you're going to do is you're going to define the first function, which is called init. Those are 2 underscores before init and 2 underscores after init. And this is the procedure that will run every time you create a perceptron. So this is essentially, we'll initialize your perceptron. And the arguments are self and number of inputs. And you put a colon, and there you go. I could try to explain what self means. Self is a variable where the object can refer to itself. If you don't understand that, it's not really that important, but just know that the self is like talking to yourself, and so when we create an object and we talk about self, it's talking to itself. So as you can see on the right here, the first variable with respect to creating a perceptron is how many inputs are there. And we have n inputs, so that's what we're going to put in there. The next thing is the weights, right? So we're going to create a list of weights. Just like that. Oh, sorry, like that. And what this is a list of weights, and we're going to load it up with the weights that go with the perceptron. The next thing is we're going to save the...
Is that a list or a dictionary?
Oh, thank you. Thanks to whoever caught that. So there are obviously some people who know how to program in Python here, so that's good. When I make mistakes, just yell it out. All right, and we're also going to save the number of inputs that we get that we pass in here. And all this line is doing is it's saying, so we're going to create a perceptron, we're going to pass through the argument of the number of inputs, and we're just going to save it in there. All right, the next thing we're going to do is we're going to loop through all of the inputs, and we're going to assign numbers to the weights. So when you initialize your perceptron, what you want to do is you want to assign a random value to each one of the weights. Would anyone here happen to know why you wouldn't assign all the weights to be 0 to start? Obviously, this is assuming that you actually would have some knowledge of this sort of thing, so we're going to get to that. But Nathan, do you know?
I think it has some, like, so say if you initialize them all to 0, I think it has something to do with the fact that when you do the more propagation, they all change in the same way, and so it becomes harder for it to train. So if you do random initialization, they can converge faster, I think.
That's correct. So if you didn't hear, basically, if all the weights are set to 0, during the training process, it can get stuck. But by making the weights random, then as it's learning, the weights that are more towards where they should be or in the other direction, they can kind of move in the direction that they need to go, and they can separate, and your model can converge on the solution. So to do that, it's pretty straightforward. So we're going to loop through all of the inputs, and we're going to say self.weights. I'm just going to type this out and I'm going to explain it. Times 2 times 1.
I'm just curious, if you did, by mistake, set them all to 0, what kind of error would you get to be able to troubleshoot that?
So if you did set all the weights to 0, what error would you get so that you would know that? So it's possible you wouldn't see anything. It's possible that what would happen is it would just might take a little while longer for the network to train than it might otherwise, which is something that you wouldn't necessarily notice. I guess in a certain rare case, depending on how the data looks, it can get stuck and then it wouldn't train at all and you wouldn't see any progress. But this is a pretty easy thing to do to initialize your weights. And basically what I'm doing here is I'm going through every weight. Random.random gives you a number between 0 and 1. You multiply by 2, you get a number between 0 and 2. You subtract 1, you get a number between negative 1 and 1. And it's going to be a floating point number. And just to see that it works, I've stepped back one here. Let's just print the weights to see if it works. All right, so there you have it. You can run it. If it runs successfully, you'll see this number here. And if I create a perceptron, let's say P equals perceptron, and let's give it 5 inputs, you get 5 weights. So these are 5 random numbers between negative 1 and 1. 0.4 minus 0.05, 0.87, etc. Okay, so anyone having trouble with that? The next thing that we want to do here is, so we've got the inputs, we've got the weights, so the next thing to do is pass it forward through the perceptron. So we're going to define it. Go ahead.
You're not putting any English, like a bias vector in B?
You're ahead of me. Yeah. We'll get there. So the initial, this perceptron will not have a bias, but we will get to that. So let's just do create a method called feedforward. And again, it's self. And this one is actually takes in the actual inputs. So init took in the number of inputs. This one is going to take in a list of the actual inputs. So x0, x1, x2, and so forth. And we're going to want to use those later. So let's save them. And so the first thing we're going to do is we're going to set the sum to 0. And then we are just going to loop through. Okay, I'll slow down for a moment. Oh, thank you. That's better. All right, we're going to loop through, and what are we going to do? For each one of these, we're going to increment the sum by the weight times the input. Fair enough, you know, all right. Yeah. So the question is, so this is being recorded, and I think Laura's going to post it on the YouTube channel, and there'll be a link probably in the meetup. So, all right. So what have we done here? We're gonna, I is gonna loop, it's gonna go from 0, 1, it's gonna loop through the number of inputs, and for each weight, it's gonna multiply by the actual input. So if you pass in 3 inputs, there's 3 weights, multiply them, sum them all up. All right, the next thing that we're gonna do is, so back up 1, we are going to take the output, so basically the sum, and as you can see, we're going to take it and we're going to pass it through the activation. So to do that, we're going to take self that output, and we're going to self that activation, and we're going to pass the sum in. And then the output we're going to return, the output of this whole method is we're going to return the output. All right, now what we're missing is the activation. And then we'll have our basic perceptron. So we're going to define the activation. It's going to be a function of itself and some value that's passed in. Let's call it x. I suppose I could have called that sum, but call it x. So if x is greater than 0, we're going to return 1. Otherwise, we're going to return 0.
Your size is greater than or equal to 0.
So yeah, so here what we're saying is this activation function, which is the step function, it takes in a value, we're going to call it x. If x is greater than 0, if x is greater than 0, we return 1. And if it's less than 0, we return 0.
So it's the discrepancy between the slide and the implementation.
For the 1, it says, so here it says if x is greater than 0,
Equal.
Oh, okay. I see what you're saying. Greater than or equal to. All right, so to go ahead and hit, once you're done with this, go ahead and hit Shift Enter, and that should get you to. This is really hard with this screen, so I wonder if I should open this up. That'll be better. And I'll just switch back and forth between this and the presentation. Okay, so we've just updated our recipe for the Perceptron. So let's create this guy anew. So just hit Shift Enter. And now what we can do is we can see if it works. So let's type feed forward. And it needs 5 inputs. So we'll do 1, 2, 3, 4, 5. And this is what happens when you make an error.
So input values are 1, 2, 3, 4, 5.
Because these are plural.
So the weights is plural? Is it one?
Yeah, weights is plural, so. So this this output is either going to be a 1 or 0, depending on what the random weights are. All right, I'll pause for a moment and ask if people are lost or if anyone has any questions about what we've done so far.
So where is a step function output actually used in practical world?
So let's talk about the practical world while people are catching up on this. And you know what? I'm just going to roll this back up a little bit, just in case. Maybe I'll make it one thing smaller. Hopefully people can read that. All right. So for people who've taken Andrew Ning's machine learning class on Coursera or any other classes, you know that when people do machine learning or deep learning, they don't create Perceptron classes like this. Instead, what people do is they use matrices and matrix math. And people are nodding their heads yes. Are you a sojournist with the beard?
Yes.
Why are you nodding your head yes? Why? I beg pardon? Okay. Why do people use matrices instead of actually creating a class for each node in the network?
There's a lot of libraries which...
But we got them back here. Go ahead.
I would probably use like matrix map to make it
Why?
and faster.
Faster why?
GPU. Think of like after compiling and everything, just the way that it can be handled is a lot easier than like doing loops and doing things that are sequential.
So we have an answer in the front here. Go ahead.
You could use a GPU.
It's the GPU. So
Matrix operations are
the matrix operations are much faster on the GPU because you can parallelize the whole thing. So this does not take advantage of that. So that's number one. In practical world implementations, no one would do it this way. The reason why we're doing it this way and why I thought this was interesting is because when you do it this way, you can actually get some interesting insights into how it's actually working. At work, I would suggest you do not do this. And the other question that you had with the step function, my guess is that the step function is probably never used ever. But again, the reason that we're using it here is because it is the simplest activation function there is. And it's a good place to start learning. So it's obviously very easy to implement. In 4 lines, you can get it, and it's easy to get your head around. So is everyone up to speed on this start here? Okay, so we've got this Perceptron, and I want to put it through the first task. Right, we actually want it to do a thing, right? So, the thing that we're going to do here is we're going to put together, I got a slide on this. All right. Is that, you know what, I'll make it full screen. So there we go. All right. All right, so here we got a graph that goes from 0 to 1,000 on the x-axis, 0 to 1,000 on the y-axis. This is going to be our domain that we're going to work in. And on it, we have a line, right? And so this line, the equation of this line happens to be y equals 1/2 x. And the first input to our perceptron is going to be the value of the x-axis, and the second input is going to be the value of the y-axis. And so what we want to do is train this perceptron to learn if the point is above the line or below the line. So the first thing we need to do is create a line. Any questions about that, by the way? Okay, first thing we need to do is create a line. So define line, you feed it in a value, and it's going to return 0.5 times x. Hit Shift Enter. And so if I said line 10, 5. So it works. we're going to do something else here because this is going to be useful in the future. Oh, okay. For people who aren't familiar with Jupyter, let me just take a step back and like help you out because I hear some talking. I don't know if this is a particular problem or not. There are two modes in Jupyter. As you can see on the left, the bar is green. See on the one, that's the edit mode, right? If you hit escape, you go into the command mode and it's blue. In the command mode, you can type A and it'll put give you a cell above, and you can type B and it'll put a cell below. So that might be helpful for you. So this function here that's going to graph, this has nothing to do with neural nets, right? This is just purely some Python so we can actually visualize what we're doing. So I'm not going to explain it in too much detail. It kind of stinks, you just have to type this, but it's actually pretty short. So what we're going to do is we're going to create an array of numbers that goes from 0 to 9999. That's going to be our x. Our y is going to be whatever formula is passed through, times all those, or as a function of all those values of x that we just created. We're going to plot it. Yeah, so this bit here is just Python.
Formula.
Thank you. All right, we're going to plot it. Oh, so we need to set up the x-axis. Make sure that it goes from 1 to 1,000. And we're going to do the same thing with our y-axis. Make sure that that goes from 1 to 1,000. And then we're going to show the plot. So, all right, so that's not too long, hopefully. But if I were to do something like graph the line, hopefully that worked. And there it is. So I'll go back up here so people can. So this, just type it. Everyone got it? Anyone not have it? All right, I'll give you a moment. Actually, while that's happening, if I just move this. There it is. I want to go back to the slides. 2 monitors would have been awesome, but I suppose that's okay. So this sort of task, I don't know if people have heard of classification before, but essentially what we're going to do is this perceptron is going to be a classifier. So given a point, it's going to classify it into one of 2 classes, either above the line or below the line. And it's a linear classifier, obviously, because it's a line. So this is also something that's called supervised learning. And there are 2 main categories of machine learning, supervised and unsupervised. Supervised learning basically means that you're providing data and you know the answer for each bit of data that you provide. And in this particular case, it's very easy for us to know whether the point is above the line or below the line. So we can actually tell the network, when given a point, whether it is above or below. And you'll see that we're actually going to do that in a moment. And so unsupervised learning is when you provide some data to the network and you don't necessarily have the answer as to what it is, and the network just generally finds interesting things in the data for you. Like one example of unsupervised learning would be something like anomaly detection. So, given a bunch of data, if you have like a stream of data, and you want to know if there's any points of data that look like they don't fit, that would be anomaly detection. So that would be something unsupervised. So we got the graph. Are we good over there? You got, okay, good. All right. All right, so let's build a perceptron that's actually going to do the thing that I said that we're just going to do. So we're going to say P equals perceptron. 2 inputs, obviously, right? We've got the x coordinate, it's going to be the first input. The y coordinate is going to be the second input. That's how we're going to put in our point. That makes sense, right? That's what happens when you don't pass an argument. That's what happens when you do pass an argument. All right, so let's take this perceptron and see if it works. So we haven't trained it, right? So we already know that it's not going to work, but this will be useful. So we have our inputs, the 2 inputs. We're going to produce the output by doing the feed forward. So if I were to create an x coordinate and let's choose a random number between 1 and 1,000. And let's make a y coordinate between 1 and 1,000. Now the line, so let me go back over here. All right. So x coordinate is going to be on this line, y coordinate is going to be on this line. The point on the graph, or I'm sorry, so the point on the graph is going to be the x coordinate and the y coordinate. The point on the line, so basically going down vertically, is going to in fact be the x coordinate of the point as an input to the line. So if I were to do the line of y is equal to the line of the x coordinate, here we'll have a point. So let's just print it out. I'm going to print it here. And then I'm going to talk about this. All right, let's see if it works. Okay. So, if you stay on this cell and you hold control and hit enter multiple times, you can go through in multiple instances. So, the first line, this 689 and 281, those are our 2 random numbers. That's a random point. The random point is at 689 around here, 281, so it's around there, right? The point that's on the line is going to be 689 and 344. So this point is it above or below the line?
No, it's below.
It is below the line because the point is at 689, 281, which is about there, and the line is at 689, 344, which is right there. So let's do another one. Ah, that was too close. All right, let's do this one. Yeah, so this one is at 622, which is here. The point is 622, 693, which is like up here. And the line is at 622, 311. So the point is above the line. So if we were to do this, we can actually have our system tell us whether it's above or below by just saying if the y-coordinate is greater than the line y. So the y-coordinate of the point and the y-coordinate of the line. If the y-coordinate is above the line, then you have your answer equals 1. It's above. Else, your answer equals 0. And at the end, we can print the answer. All right, let me scroll down a bit. Let's see if this works. So, this one, the answer is 1. The point is at 858,724. The line is 858,429. So that is the correct answer. Still above. How about that? If we were in Vegas, okay, here we go. And so here, this one's below. The point is at 503.21, which is like there, and the line is at 503.251, so it's 0, so it's below. So the next thing that I want to do before we start training this thing is to let's figure out a measure of how good this random perceptron is. And we can do that by essentially let's run 1,000 points through it, and let's count up how many times it gets the right answer versus the wrong answer. So if we were to start with the number of correct answers equals 0, and we're going to go through, we're going to do 1,000 times. Oops. All right. Now, let's copy some code just to save ourselves from some typing. So this is helpful here. And I will go down here and paste it in. By the way, in Python, it's very important to get all your tabs right. I'll get very upset if the tabs are not corrected. All right, so first thing we're going to do is we're going to get a random point, and then we're going to find the point on the line, just like we did before. So, is above is going to equal, like we saw earlier, if the y-coordinate is greater than the line y. So, if the point is above the line, is above will be true. And if it's below the line, it'll be false. So the next thing we're going to do is we're going to ask our perceptron what it thinks. And the way we're going to do that is we're going to feed the point into it, and we're going to ask it, is it above the line or below the line? And what we're going to do is we're going to feed in, let me open this up to full screen. We're going to feed in the x-coordinate and the y-coordinate, and that's going to be the guess above. And since our it wants a list of the inputs, so there you go. So it's a list of two numbers, the x-coordinate and the y-coordinate. And then what we're going to do is we're going to say if is above is true, like that, and the guess above by the way, do you see that sometimes I type really fast? So in Jupyter, if you hit tab, it will auto-complete the functions for you. So that's one way to go through them very quickly. So if, basically what we're saying here, if is above is true, so it's above the line, and the guess. Now I chose 0.5 here, right? Which is never an output of the perceptron. What are the outputs of the perceptron? Does anyone remember? What are the possible outputs?
0.
0 and 1, that's it, right? It's a step function. So if the hypothesis is greater than 0, the output's 1. If it's less than 0, it's 0. So I could say, and guess above equals 1, and that would do the same thing. But I've said is greater than or equal to 0.5 here because we'll get to a point where the output won't be just 0 and 1 when we move away from a step function. So this is easy enough to understand. If it's greater than a half, and we know that it's 1, then in fact, that actually increments the number of correct answers. So this is almost done. If is above is false, and yes above is less than 0.5, then once again we're correct, right? Plus equals 1. Let me scroll up a little bit here. Just really quickly, just to review, we're going to loop through this 1,000 times. Every time we loop through it, we're going to pick a random point, the x-coordinate and the y-coordinate. We're going to find where it is on the line, just like we did in the cell right above. If is in fact above, then is above will either be set to true or false. And that's actual the reality, right? So, because we know this for a fact, the point is above or below the line because we actually computed it. This guess above, that's our output of our perceptron. And the perceptron is actually going to take in the input and it's going to tell us. The output is going to be 1 if it's above, 0 if it's below. And we're going to, and if the reality is the same as the guess, we'll increment the counter. And so if you run this, what you end up getting is, oh, you know what? We forgot the very last thing, which is to print. Correct. All right, so there we go. So out of 1,000 tries, it got 360 of them correct. And that feels like it's not particularly very good, is it? And you wouldn't really expect it to, because it hasn't been trained yet. The weights are random. If you've gotten this far, then you could scroll up, and you could shift enter on this cell, make yourself a new one, and then come down here, run this again, and you're going to get a different answer. And if you wanted to, you could just go to this, and even with the same perceptron, run it multiple times. Why is this different every time? Why is it not always the exact same number?
Isn't the random initialization?
No, sorry, but it is. It has to do with random though, but good guess. Does somebody else have an answer?
You need a seed.
Beg your pardon?
You need a seed to repeat the same number.
So a seed is something that you can use to make sure that the random number is always the same, but they're not. We haven't used a seed. So why would this be 367, 372, 407?
XY coordinates. We are randomizing them.
Right, because every time we go through, we choose 1,000 random points, and the number of those random points that's above the line or below the line is going to be different each time, and whether or not the perceptron gets them right or wrong will be different each time. So, but raise your hand if you haven't gotten this far. If you're not up to this bit here. Okay, the next thing that we're going to do is what? What's the next thing we're going to do? Anyone?
Train.
Train! Exactly. We're going to train. So, coming back to here. Boom. All right. We've gone through here. So, we've set this up. We've built this. This is our perceptron so far. The data is going this way. Feed forward. Forward propagation. The inputs come in, we sum them, activate, output, right? How do you train? You train by going the other way. So some people are nodding their heads, they're familiar with this. So we're going to enable the perceptron to learn from its mistakes. So, you have the same inputs, X coordinate, Y coordinate, but the output is no longer the output. Instead, what we've got here, what we're feeding in the other direction, is not the output, but the error. And the error is essentially how far is the guess from the actual value. We know the actual values because we can compute those. We know whether a point is above the line or not. That's the supervised portion of the learning. And we know what the guess is. So subtracting the actual value from the guess will give us the error. And then we can feed the error back in the other direction. So if this is the same, we have the summation, we have the activation. But this is the key. This is the whole key to training a neural network, and specifically with this perceptron. And that is that the error is going in, and the error is going to be a quantity this big, right? However it is, right? It's going to be a certain number. And we're going to split the error across all of the inputs. And we're going to split the error across all of the inputs as a function of the size of the input. So, if this input here is 10, and that input there is 5, then 2/3 of the error is going to go that way, and 1/3 of the error is going to go that way. And the reason that we do this makes logical sense because if you have a perceptron that is producing an error, chances are that it's the input with the biggest, that's the largest input that's actually contributing the most to that error, and that's the one we want to adjust the most. So what we end up doing is adjusting the weights. And as I mentioned at the beginning of the workshop, the whole purpose of the training is to find the magical weights that are going to produce the answer that you want. And so we're going to adjust the weights based on the error that goes through each of these branches. And that is essentially going to be the error times the size of the input, the x0. So for this branch, it's the x0. And for this one, it's going to be the error times x1, because that's the size of this branch, times alpha. Alpha is called the learning rate. And that can use a little bit of explanation. The idea here is that in marching towards our destination, which are the perfect weights, we want to take little steps, little baby steps. And so we multiply this error by this small number, which is the learning rate. In this particular case, it's 0.01, right? The actual value of the learning rate can be different things. But many people, including myself, when you first hear about the learning rate, you might say to yourself, oh wait, let's crank it up. Let's learn fast. Why 0.01? Let's make it 100, 1,000, 1,000,000, right? So it's a little bit of a misnomer in that sense. But it's important to know that you want a small number because you want to take little baby steps towards your goal. If you take big steps, you could jump right over your goal. So what is the right learning rate? It depends. Depends on many different things. You experiment, you figure it out, you play around, you try different things. 0.01 is just like a very standard thing that people use for lots of different things. If your learning rate, so let me throw out some questions. I said that if your learning rate is too large, you might jump over your answer, which means you actually won't get it. What if the learning rate is too small? Anyone know what happened? Maybe a new person who hasn't answered the question yet? And all the way in the back.
It'll take a long time to convert.
It'll take, yes. So it'll take longer to convert. So we could make the learning rate 0.0001. We're definitely not going to jump over our answer, but boy, it's going to take a long time to get there because the steps are going to be so teeny tiny. So yes, thanks. So, all right, let's do it. Let's train this thing. Coming back here. All right. if you wouldn't mind, scroll all the way back up to your Perceptron class. And we're going to add in the training. So let's define something called the backward pass. And in it, so again, we always use self. It's an object-oriented thing. If you don't understand what it means, it's cool. Don't worry about it. But into the backward pass, here, we pass the error. Right? And the error is going to be this, but that's what we're going to pass back into it, right? But assuming this function gets the error, what are we going to do with the error? So the first thing we're going to do is we're going to set our learning rate. Now, people who are familiar with programming might say, wait, you're putting it in the method, you're going to run it every single time. And that's true, but you know what, it's okay. We have fast computers. So it can be optimized later. Laura's looking at me, why is that there? You should just assign it once and call it a day. But it's there, it's okay. It'll remind us where it is. So, as I mentioned, we're going to split the error across all of the inputs. How many inputs do we have? We have num inputs, self.num inputs. This is the number that was saved in the very beginning when we created the Perceptron. Let me just go up. Right there. We initialize the Perceptron with the number of inputs. It's saved right there. So in this particular case, we've got 2. So this one is going to go 0, 1 for the two inputs. And what we want to do is we want to adjust the weights. So we'll go through the weights one at a time, and we are going to subtract from it. There we go. We're going to subtract from each weight. So the first weight, we're going to subtract the error that is passed through times the input times the learning rate. And while we're here, we're going to do one more thing, which is going to be easy. And I'm just going to define a function called getWeights. And the reason why I'm going to do this is because our weights are changing, and I'd like to look at them. So all this is going to do is it's going to return the weights. Oh, all right. So I'll let everyone catch up there. Raise your hand if you're not there. All right, I'll give it a few more minutes. Oh, so while people are typing that in, am I blocking? Yeah. I'm blocking. Let me go back here. Hold on. There we go. All right. Nathan.
Do you not need to initialize self.error equals error?
Okay, good question. So in the backward pass, I'm actually not saving the error. And the reason is because I'm not going to need it after I use it. So we're going to take the error, we're going to pass it through, we're going to adjust the weights, and then throw it away. We don't need it anymore. The things that we need to save are the inputs, because obviously that's what we use to weight the error across the various inputs. We need to save the weights. Those are important. So that's why we save those. But the error, no. So this is going to be the easiest question of the evening. So someone who hasn't answered one should jump in right now. So when we fed in the data here, and we fed it through that way, Nathan told us that that's called the forward propagation. Anyone have any idea what it's called when you go the other way? The backward propagation, exactly. And if you want to be really cool, which I know you all do, call it back prop. And then people are like, no, okay, that guy, he knows this stuff. All right. Here's a question which, just out of curiosity, which maybe someone will know. I'm sure some people know the answer to this. So this term alpha, anyone know what sort of class of variables that's referred to as?
Bias.
It's not the bias.
Hyperparameter.
It's called a hyperparameter. In general, a hyperparameter is a value that you set before the training. All the other values are learned during the training. There are many different things that are hyperparameters in neural networks. The batch size, the learning rate, number of layers, the size of the kernel, if you're doing like the convolutional net, or all kinds of different things. But basically, these are variables that you use to set up the model. So back in software 2.0, when there was that graph and there's the initial point that you start with, those are defined by both the model and the hyperparameters in the model, and then you go through and you optimize. So if people are, is anyone still doing the backward pass? Okay, good. So this is a Jupyter thing. So when you update the class Perceptron, it doesn't know that it's updated until you actually run it. So you have to hit Shift Enter to run it. And now we've updated the class. The other thing that it doesn't know is this Perceptron here, Perceptron 2, it's the old one, not the new one. You got to run that again too. So you got to create a new one. So now we've got a new P. We can remember this code here. We can see how well it does. It does terrible. So let's train it. All right. And this is the moment you've all been waiting for. It will automatically figure out exactly what it is it's supposed to do. So, you train a network, or a node in this case, with data. And typically that data will reside in a file, or it will be somewhere. In this particular case, we're not going to do that. We're going to do something, we're going to create synthetic data. Or basically we're going to generate the data. And we're going to do that by just creating a loop, and we're looping through, and just like we did previously, we're going to create some random points, and we know whether those points are above or below the line, because we know the line, and so we'll do that, and then we'll feed the error back in. So, to save ourselves some time, we're going to grab this code here. And we'll grab this code here. I'm going to type that in, right? So what this is doing here is it's saying we're going to create 1,000 random data points. And we get the random point, we get the line on the point. We need to know what the real answer is, right? And the real answer is if the y coordinate is above the line, then we know that the real answer is, what is the real answer?
1.
1, exactly. If it's not 1, then the real answer is, what's the real answer if it's not 1?
0.
It is 0, exactly. All right, that's what we know the answer to be, right? We're going to get the guess again from the network. We're going to feed into it the x coordinate and the y coordinate, right? This is the guess. And then what we're going to do is we're going to feed the error into the backwards pass, right? So the backwards pass is this. And the error is very simply the guess minus the answer. And then at the very end, what I'm going to do is, after all the training is done, let's just print the weights. All right, should we try it? What did I do wrong?
You don't have a P1000, do you?
This is what I did wrong. Okay. So, our weights were initially up here, minus 0.36, minus 0.62. We've trained it with 1,000 data points, and look, they've changed. Which is what we'd want. Did they change in the right way, or did they change in the wrong way?
We don't know.
We have to have a way to figure that out. So I'll give a second for people to catch up here. I notice people are still looking at the screen. Previously, the cell right above this one, we actually wrote some code to test the untrained perceptron, and it did terrible. Well, now we trained it, we can go back and do it again. So if I were to scroll up here, go back to this one, see correct equals 0. Last time it was 261. This time, well, there we go. So we got one wrong, but 99.9% accurate. If I do this like a few times, oh, well, how about that? So pretty good. Is everyone here this far? Let me know if you're not. You need a few more minutes there? Okay. While those folks are maybe typing in, let me just review what we did here. By the way, this is a Python thing. For blank in range 0 to 1,000. Basically, this means we're going to loop through this 1,000 times. But we don't care what the counter is. That's why it's blank. It could be I or A or X or whatever. For blank. So we're going to loop through this 1,000 times. We're going to get 1,000 random points. The X coordinate, Y coordinate, that's our point. Just like we did previously, we're going to get the line. Where is the line? The point on the line. And basically by feeding in the X coordinate of the point, we get where the line is into our function line. This right here is the real answer. It will tell us if the point is above the line or not. If it's above the line, the answer is 1. If it's below the line, the answer is 0. So this is the real answer. This here is the guess. We go into the perceptron and we ask it, is it above or below? And it's random, so it'll start by just giving a random answer, yes or no or whatever. And we know, as we saw, that it's frequently wrong, right? So what we do is we take the error, which is whatever it guessed, minus what we know it is, and we feed that back in. So if the point is above the line, yeah, here's something we can look at. While people are catching up here, this is something we can think about. If the point is above the line, and the answer is 1, and the perceptron comes back and gives you the answer that's 1, the error is 0. We're going to feed 0 back through the backward pass. How much are the weights going to change? 0. Nothing. So, just like in real life, you only learn from your mistakes. Right? Isn't that just like real life? So, if the perceptron gets the right answer, the weights don't change. If the real answer is 1, and the perceptron responds with a 0, we're going to feed the number 1 back, and we'll adjust the weights in a particular direction. If the real answer is 0, and the perceptron returns a 1, then the answer is -1, and we feed a -1 back, and we do it. So I hear some people chatting, maybe you're not caught up, or you are caught up. You need another moment. Okay, while you're doing that, let's graph this. All right. So I'm going to go here and I'm going to do another line. So we can graph the line, right? So we've already done that. Right? But what I'd like to do is graph what the perceptron thinks the line is. And this is the part where you can actually, where I think by doing it this way, where you're building a class of a perceptron, it enables you to get a little insight into how things are working on the inside, because we can actually go in and do that. And so let me show you how that's done. So I'm going to move this over to the side, like I did. That's not what I wanted to do. I wanted to go like this. Oh, okay. So I'm going to leave that there. Wait, that's not what I want to leave there. There we go. I'll leave that there. So this is the training. You know what? If we were good developers, you know what we would do? We would comment things. Training loop. Right? That's what good developers do, right? Any good developers in the room? No? Anybody comment their code? Yeah, I don't have it. Okay. I once heard that the code is hard to write, should be hard to read. So, all right. Back to our graph here. Here's the perceptron. It's a very simple one. Takes 2 inputs, produces an output. Here are the training points. Now, what I've done here is I've run this previously, and after training and getting, after training with 1,000 data points, which is what we just did, these were my weights. I got W0 was -18 and W1 was plus 36, right? Since we actually know what the hypothesis function is and the activation function, we can actually go backwards and figure out what the line looks like. And so here, we know that if the x-coordinate is x0, we know that it's going to be multiplied by w0. So we've got minus 18.29x. And to that, we're going to add summation, the weight of the second input. And we know the second input's y. So plus 36.82y. Set that equal to 0. Why? Because that's the inflection point of the activation function. We know that at 0, that's where the output's going to switch from 0 to 1. So let's figure out what exactly is that point. And so solving, using some high school math, solving for y, I got with this, y equals 0.4969x. And that's what gave me 99.9% accuracy. The actual line is y equals 0.5x. So this is pretty close, right? Question?
I thought we were estimating only one parameter, that 0.5, right?
Which parameter?
We were estimating W0 and W1.
I'm sorry, what's the question?
Are you estimating W0 and W1 two parameters, or are you estimating one parameter, 0.5x? The 0.5 is the 0.5x.
I'm not sure what you mean by estimating, but
So the perceptron will be trained to find the weight of one weight or two weights?
2 weights. So this perceptron has 2 inputs, x0 and x1. x0 is the x-coordinate, x1 is the y-coordinate.
Why should it be this trained to find one weight, which is the ratio?
Okay, so the problem that we constructed is the one of the point in the line. And we just happen to know we set the line equal to y equals 1/2 x. So that was the construction of our problem, right?
So basically you're estimating the bias as well, right? The original question I had, like you're estimating the
bias is coming next. There's no bias here. So this is purely a 2-input perceptron. It takes the x-coordinate of the point and the y-coordinate. And I think the takeaway from this, which I hope people kind of feel, and the thing that makes neural networks magic is that we constructed a problem where we've got a graph that goes from 0 to 1,000, 0 to 1,000. I fabricated a line that is y equals 1/2 x. Could be anything. Could be any line that goes through the origin because we don't have bias. So, but any line that goes through the origin could do that. And by simply by the perceptron, by simply guessing numbers and guessing, the perceptron figured out the line without ever telling it that the line is y equals 1/2 x. And the purpose of this slide here is to show that by taking this perceptron that knows nothing of the world, jamming 1,000 points through it, telling it every time it gets it right and every time it gets it wrong, it adjusts the weights in response to that, and then, as a result, effectively figures out the line. And we know that because by reverse engineering the equation that describes the hypothesis and going backwards by doing this math here, by basically saying, we look at the outputs of the weights. I mean, you can do this yourself, right? So on this particular example right here, my output is -19 and 39. Okay, so when I put this slide together, it was -18 and 36. So pretty close. And putting that equation together, -18x plus 36y, solve for y equals 0.4969x, which is very close to y equals 0.5x. And the perceptron arrived at that without ever telling it what the actual line was. It just observed the data and converged towards that line.
Mark,
and that right there is the magic of the perceptron.
You mentioned that in attributing the error in the backward propagation, you assign more of the error proportionally to the higher number.
Yes.
Does that only work for a certain class of input output, or is that kind of a general?
This is very standard. This is very standard. When you're feeding the error back through the network, when you feed it backwards into a perceptron, you're gonna weight the error across all the inputs based on the size of those inputs and adjust the weights accordingly. So this is not like special for this. This is, step functions, not standard. This, very standard.
I think what you might be asking is, you have the calculations for W0, W1 on the one hand, and you have the slope of the line on the other, and what's the relationship? And I think it's W0 over W1 is the approximation for the slope. Is that correct?
The approximation for the slope, as it turns out, and that's actually a good way of thinking about it because we're about to do this, the approximation for the slope is negative W0 divided by W1. That's the approximation for the slope.
And that's the relationship.
And so we are, yes, and that is the relationship with the lines. And that's just a mathematical result of what we're doing here. And so the perceptron is being trained to find those values of W0 and W1, and it just so happens that they converge on the line. And we can actually see this happen, and this is kind of cool, and this is in fact the thing that's not in the GitHub, which actually I did last night, just for you all, because it's cool. Actually, I did it for myself too, because I'm kind of greedy that way. All right, let's go back to the graph. The graph here, okay, the graph formula. So if you go find that. So into the formula we pass the line. What I would also like to do is I would like to pass some weights and graph the second line. So this is the line that the perceptron thinks is the answer. So just in the input, we're going to go weights and set it equal to an empty list. The reason you do that is because if it's not included as a parameter, then it'll just assume that it's empty. But we're going to pass in some weights, right? So right after this, plot x, y. Again, this is Python stuff. So actually, you know what? I take it back. This is not Python stuff. This is Perceptron stuff. So this is actually worth knowing. So if the length of the weights equals 2. And basically what this means is, if we run this formula graph, and we actually pass in some weights, and the length of that is 2, which basically is what we're doing, right? So we're going to do something special here. And that is we're going to draw a second line. So y2. And y2 is going to equal to negative weights 0. This is the thing we just talked about 2 seconds ago, so thank you for bringing that up. Negative weights 0 divided by weights 1 times x. And this, I'm sorry, what is your name back there?
Rajiv.
Rajiv. This Rajiv is the implied slope of the line. So essentially y equals the slope times x.
Right. I'm just saying that that's normally what you are estimating as the value of the neuron, right? That's like the one value that you estimate, as opposed to two values.
Yeah, I think there might be a disconnect here because really the perceptron is estimating two values, weight 0 and weight 1. And the line that represents is y equals negative weight 0 over weight 1 times x.
Now when you extend this to with a bias, you will actually have another value, which is...
You love bias. You know what? We're gonna get to it momentarily.
I'm thinking in terms of the wx plus b is the normal way to do a
Yes. There's no bias here. Right? There's no bias.
We're to that wx, if it were just a single input neuron like you have, the w will be just one value.
Mark, I think the confusion is, you showed that initial chart that you bookmarked, which was, typically you have data plus program equals to output.
Oh, right, all the way at the beginning.
Right. Here you're saying data plus output equals program. You're trying to come up with the program.
Yep.
The weights are the program.
The weights are the program.
Correct.
Exactly.
So you're not trying to replicate the output. You're trying to replicate the.
Let's go back to that because that's where. So thank you, Andre Carvalho, for this. Right. The initial dot here, right, in software 2.0, the initial dot is our model. And this model is very simple. It's a single perceptron, has two inputs, x coordinate, y coordinate, and the output is, of course, whether this random dot is above this contrived line that we had, right? And this process of optimization, where we're zooming around there, is the training that's going to arrive at this point right here at the end. And when we get to the end point, which is what we did when we trained it, we have a program which, given a point, will tell you whether it is above or below the contrived line. And so this line that we're using goes through the origin and has a slope. So it's of the form y equals slope x. The slope, as it turns out, is mathematically equivalent to the minus weight 0 divided by minus weight 1. And the reason that I'm going to maybe do this one last time, the reason that it is like that is because, all right, if you look at this graph here, we don't have n inputs. We only have two. We've got these two, right? So this function here is in fact not all that. It's just that. The hypothesis is x0 times weight 0 plus x1 times weight 1. x0 we know is the x coordinate of our point. x1 we know is the y coordinate of our point. So this is the equivalent of weight 0 times x plus weight 1 times y. Now, we happen to know that the activation function inflects at 0. So if we take x times weight 0 plus y times weight 1, set that equal to 0, solve for y, we get y equals negative weight 0 divided by weight 1 times x. And what you're, again, there's no bias in this one. So.
Might be helpful to think of the bias as the y-intercept. So in this case, it's actually a bias of value of 0. And by changing the value of b, the y-intercept, it's a vertical translation of that line.
So what time is it? It's 8? I can go till midnight, but I don't know if everyone wants to be here to midnight. You cannot. So I don't know what time we can go, but the very next example is this plus bias. So since we keep talking about it, maybe we can do the next one. What time can we go till?
Well, we're here till 8:30. We did want to leave room for people to mingle, but if you guys are more engaged, let's continue with the workshop.
If you guys want to mingle, we can cut it. If you guys want to see bias, because it just seems like people are dying for it, then we can do that.
I want to see some bias.
All right. All right. So here we are. We made this graph. I'll accelerate just a little bit. So I was going slowly at the beginning because I didn't want people to fall off. But you know what? If you fall off now, you only got half an hour, so just hang in, right? All right. So I updated this graph to plot the line plus the function, right? So I'm going to update that like that. All right. Now, if I go down here and I say, let's graph the line and let's add the. Let me make sure I get this right. Okay. P dot get weights. Oh, I wonder if that's going to work. Oh, look at there, it worked. Okay. It's so close, it's like right on top of it. So, to get a better sense of what's happening, let me go up here. Let's create a brand new Perceptron that knows nothing. And let's graph it. Now, okay. The reason why you're not seeing anything here, can someone guess why you're not seeing the second line?
You didn't pass anything, really?
What'd you say?
You didn't pass anything?
No, it's actually, it took me forever to figure this out. It's kind of stupid. Okay, so the Perceptron is initialized with some random weights. So it's basically guessing on what this line is, right? And has no idea. So the reason we're not seeing it is because it guessed something like this. Right? So let me make another one, and let's see if it shows up. Because I kept on doing this. I'm like, why is this always blank? Let me grab another one. They're both positive. That does not work. So let me try. There we go. Both negative. Let's see if that works. Probably not, because it's still going to be the other way. I need a positive and a negative. There we go. What do you think? Think that'll work? Gosh darn it.
Can you initialize the values so that the line will...
I think you didn't plot right.
You know what I'm going to do? I'm going to see if this is working. I'm going to change this to 10. Yeah, there's another problem. It's actually not, it's not graphing it. Let me go back and take
You need plot white too.
Oh, thank you. That is exactly correct. Who said that? Give yourself a gold star. Yeah, okay, all right. So I computed the line, but I didn't plot it. So plot, x comma y, 2. All right, run this one. By the way, what you're seeing right now is why people use TensorFlow, because there we go. Okay. My goodness. All right. So I created a new random Perceptron with a random weights, and those are the weights right there. And it has no idea what's going on. So the line that it guesses at is that one right there. And if we go back here to the accuracy, let's look at the accuracy. It is going to be bad. It's actually not that bad, right? I mean, it looks pretty close, right? 68%. So let's train it. Let's train it just a little bit. Let's train it with 10. All right, our weights have moved. Previously they were negative 0.8, 0.78. Now they are negative 0.4, 6.9. Let's see if the line moves. Oh, you know why it didn't move? Because get weights. Boom. All right, that's what it was. All right, let's train it a little more. So this is where it is after 10 data points. Let me do another 10. Let's see if it moves. Oh, wow. So this thing trains really quickly. All right, it's a pretty simple model. So let's start over and let me let's get a new one here. Perceptron, let me run this. Okay, there we go. This is the guess from the beginning. The accuracy is about 53%. Let me just put in, do 2 at a time. Do 2 at a time. All right, boom. And let's see if it moves. Moves a little, maybe a little bit. Let's do 5. I'm just trying to slow it down so you can actually see it doing something. Now, what happened there? Did I lose it? Oh, okay. As you can see, it's moved closer. So it disappeared for a while there. And I know what happened there. This is one of the reasons people don't use step functions as for an activation function. Because given that it's nonlinear, like it goes this and then boom up like that, the results can swing wildly, right? Eventually it's going to converge, it does, it gets to the answer, and then it's there. And as you can see, it's already pretty close. I think I ran maybe 20 training points through it, and that's all you need. So I said we're going to do bias. So let's do bias. So what does bias look like? All right, this is the one we just did. All right, let's change our line. Rajiv, right? Is it Rajiv? Is that your name? Okay. As you can see, our line is now longer going through the origin, right? So let's update our line. And we're going to say, define the line of x. And we're going to return, as we did before, 0.5 times x. But I'm going to add 500. 500 is the bias. Now, people use the term bias a lot with machine learning. And whenever you hear AI, people talk about bias. This is an area of expertise for you, right? Yeah, pretty much? No? Somewhat?
I know.
Can I call on you to explain what people generally mean when they talk about bias?
So, I mean, there's a lot of controversy around the term bias in artificial intelligence if you're talking about ethics versus if you're talking about mathematics.
Ethics.
Right.
So the ethics is?
So the ethics, when you're talking about artificial intelligence and machine learning, you're looking specifically at skewed data sets. So for example, if you have a very homogeneous group of people working on a machine learning problem, for example, they're only going to be able to really speak from their perspective and train data that comes from the data that they're exposed to, right, or from their lived experience.
And give us like a concrete example of bias in artificial intelligence in the ethics sense.
Sure. So, for example, when a lot of the original computer vision products were produced, oftentimes they were not produced to recognize individuals of color, right? Because the data sets they were trained on were just of mostly white men, and so they would not recognize, you know, black people, Latinx individuals, or anyone else.
Right, and this is an extremely important topic, and it has absolutely nothing to do with this bias. That's very important. And this bias, just to be clear, this is the mathematical bias, right? And essentially, it just means you know what? I can graph it. Graph the line, and there you go. This bias is just this distance here. It's the 500. We took our line and we moved it up 500. Mathematically, that's called the bias. And that's the thing we've kind of been talking about a bit. So, in our, I don't know if we're going to be able to get through this, but the way this works with the perceptron is previously we had 2 inputs, the x and the y. Now we've got a third input. And the third input is the bias. And you set it to a constant value. It's always 1. And so what you end up with here is your hypothesis function is going to be x times weight 0 plus y times weight 1 plus weight 2. And it's the weight 2 that enables you to get out of the origin of the problem. And so to actually do that, we will create a new perceptron. And it's going to be 3 inputs. Boom. And there they are, right? All right, let me see if... All right, I can do this quickly. So just watch me. You can do it at home. All of this will be online. So I'm just going to put it through here. So let's see how well this perceptron does with this problem. And so what I'm going to do is I'm going to copy this code here. This was the non-biased code. I'm going to pop it in there. And what we need here is, into our brand new perceptron, we need to add this. Anyone know what that's called? Please.
It's the weight of the bias.
It's the bias, exactly. So this is the bias, right? So we're going to put that in. And so this is, our line is now this. And we're going to put this in here, and we're going to, and how does it do? 742? Not so good. Let's grab another one. Let's see if we can get one that does worse. All right. Not particularly good. So what we want to do is train it. Give me 1 second, and here we are. Okay. All right, the training is going to be the same unbiased training. Where is it here? Train the loop. Fortunately, it's commented. All right. All Greek programmers comment their code. So here we go. So we're going to train this, and the only change we need to make here is that. Let's see if this works. We got some new weights. This was 612 before. All right. Oh, I trained it with 5 data points. I bet if I plug in 1,000, it'll go exactly to where it needs to go. Yeah, maybe this takes a little bit longer. Let me plug in 10,000. By the way, one thing that you can do here, which you notice that I'm doing, is that if you have a, and this is actually pretty much true for all neural networks. If you have a network, in this case it's the perceptron, and you've trained it with some data, and it gets you to a certain level of optimization to achieve a certain thing, you can continue to train it with more data. You can just keep on training it, right? And hopefully you'll continue along the optimization path. But you don't have to start over from 0 again. So, so let's see what this looks like. Let's graph it again. Graph. Let's graph the line and the P weights. This is not going to work because I need to make one more adjustment to our graphing program. So if in fact the length of the weights is 3, right? Just want to make sure I get this right. I'm speeding through this here because I want to let everybody go. Oh, here we go. Okay. This is the same, but we're going to subtract weights 2 divided by weights 1. And now I can tell you what that means. The weights 2 divided by weights 1 is derived the exact same way as I did the previous one. You take the hypothesis function, set it equal to 0, solve for y, and this works out. It's straightforward high school math. But at the end, let's see if this works.
Use get underscore weight.
Oh, can someone debug this for me?
Get underscore weight.
Thank you. Get weights. Right, okay, so this is where we are after a certain amount of training. And as you can see, I'm going to show you one last thing, right? So I trained it with 10,000. You know what I'm going to do? I'm going to train it with, how many is that? 100,000? A million. Now I got a pretty beefy machine, so that did that relatively fast. But what happened here? Come on. Okay. This orange line originally went through the origin, and now it's moved up a bit. After a million data points, it's moved up to like, looks like around 100. Let me do another million. And then the last thing I'm going to do is I'm going to explain to you why this is taking so long. Show one more. Moved up a little bit. We do one more. Okay, now we're getting closer to 200. Let's do 10 million.
Smoke coming out of the machine.
Yes. It's a good thing I don't have the Apple II. Seriously, this would take like 3 weeks just to do this. All right. You can see it's getting closer, but it's taking forever. So the last question I'm going to ask you guys before we call it is, does anyone have, and then by the way, this took me personally like hours and hours to figure out. But the answer is actually pretty straightforward, and it's also very interesting and intuitive. Can anyone guess why previously, without the bias, this thing trained in 1,000 examples? In fact, less than that. It's like 100 examples. Boom, we're at 100%. Here, I pumped in 10 million, 15 million, obviously orders of magnitude more. And the thing is like, it's getting closer. Eventually with like maybe 100 million points, I don't know, it's going to get it and it's going to be accurate. Why is it taking so long? If no one has a guess, I will tell you the answer. Go ahead.
That was actually my question. I was trying to understand how fast it converges, and like in one case you get like 10,000, in another case you get millions. It's still not close.
So this is converging extremely slowly. The previous example without the bias was extremely fast. Why? And all the way in the back. Once again?
Learning rate.
It's not, so increasing the learning rate would make it go faster, but I'm using the same learning rate with both. It's 0.01 with the bias and without the bias. So it's not the learning rate.
It's the weights, one of the weights is different than the other two. It's much bigger, it's like 500.
That is exactly the answer. So Nathan, is that what you were about to say? So this is the last thing. This is why I think that this kind of, it felt laborious like to kind of go through all this, but this is why I think like doing it this way is, at least for me personally, I find it really fascinating. And it goes back to, where's our back prop thing? That's not that one, where is it? This one, okay. So let me open this up and go to here. Boom. Okay. This only has 2 inputs. Our one with bias has 3, but imagine that there's a third one here, right? Now, as you can see, as I explained before, we split the error across all of the inputs as a function of the size of the input. Now, the x-coordinate is a number between 1 and 1,000. 1 and 1,000? Or 0 and 999, one of the two. 1 and 1,000, right? Average 500. The y-coordinate, also average value of 500, right? Because it's randomly between 1 and 1,000. The bias, which is not on here, is 1. So you have some error that's big like this, and you feed it through, and you split the error across the inputs. Only a tiny, tiny little sliver of that is going to go to your bias, which means the weight that's on the bias is going to take forever to get to where it needs to go. So, does anyone know what the solution to this is? Can you get in the back?
You want to normalize randomization
So you normalize the inputs, that's exactly correct. And so that was the next thing I'm going to show you, which I'm not going to do. But, so let me normalize the inputs, what does that mean? Essentially, you take all of your inputs, which are different ranges, like whether they're 1 to 1,000, 1 to 1,000,000, or just 1, and you squeeze them down all into the same range. So you basically scale it. And so there's actually 2 ways that you could do this. You could take your inputs for the x-coordinate and the y-coordinate, divide them by 1,000, or 500 if you like, to basically scale it down to a number that's going to be around 1. The other way, you can leave them the way they are, and instead of making your bias 1, make it 500. So they're all kind of on the same order of magnitude. And when you do that, it trends like that. So, thanks everyone for coming. For me, this was like, I mean, I love this stuff. I have a passion for it. I think many people in this room do too. So it's definitely a different way to look at neural networks. It's not standard. The class, go to Google, type a search for class Perceptron, you're like find nothing. You could probably find my GitHub account. Because it's just not done this way. But for me personally, I thought it's interesting, but I need to know what you think. So what we did not do was pretty much everything. Not everything, but there's big chunks of it. What we did not do is, we did the point in the line, we did the bias, we didn't do the logical gates, the and or, which you can do with a single perceptron. The XOR, you need 2. Normally people do it with 3, so you're actually creating a network. And then the multi-node point in a parabola is when you actually do things that are non-linear, which means you have to go away from the step function. So if the feedback is interesting, and you people like this, we could theoretically do another one that would pick up from here, but that's up to you, that's up to Laura, that's up to the timing, sort of thing. So, but regardless, I think I'll make it available on the GitHub, and I'll update this, and people can check it out. But yeah, so thanks, appreciate it.